Pavel, first of all, happy birthday. I'm very happy to participate in this event. If I remember correctly, the first time that I met you was in a field arithmetic conference in Oberwolfach. I think that when in Oberwolfach there is a traditional hike, and at the end of the hike you told me, and I think also Wolfgang was there, you took me and Elad, we were both young students, and you took us to sit with you in the cafe in one of the villages there, and you told us that we need to eat Schwarzwald Kuchen, right? And then we talked about mathematics. You told us some open problems in profinite group theory about inverse limits of finitely generated free profinite groups. And you told me that in order to appreciate this problem, I need to think about it seriously. And indeed, I thought about it quite a lot for a certain time and couldn't solve this question. Since then, I think we worked quite a lot. We met quite frequently every I don't know, a year or maybe less until COVID, and then somehow in COVID all traveling was stopped, so I didn't see you since 2019. This conference is called Profinite Groups and Applications, and this talk will be a bit aside. It relates to profinite groups, maybe to the most interesting profinite group for number theorists, which is the absolute Galois group of Q. But it will be quite aside, so I prepared a talk which is more introductory, and I will not get into a lot of details. I know that this will disappoint you, that it's not too technical, but I hope you will survive it. So let's start with, first what is Galois theory? So we have this object that is called a polynomial, and in Galois theory we take polynomial with let's say integer coefficients, and we can also write it as a product of x minus zi, where zi's are the roots and they are usually complex numbers. And we want to understand the arithmetic of the roots in terms of the coefficients. So the coefficients are given, and the roots, there are some numbers in the complex numbers, and we want to understand what can we say about the arithmetics of them without actually find them. And this goes to Galois, of course, who wanted to check whether there is a root formula in terms of the coefficients, and his philosophy was that we need to look on the group of symmetries, which is the Galois group of the polynomial. And this Galois group encodes the arithmetic information of the roots. And the point is, I wanted to give some examples. So we have a root if and only if the Galois group has a fixed point, and the polynomial is irreducible if and only if the Galois group is transitive. And for this talk, I will focus on the last property, that the Galois group is inside AN if and only if the discriminant is a non-zero square. And usually in application, in application we get a polynomial from our application. It can be from geometry or arithmetics or number theory. We get a polynomial, and in order to say something interesting, we need to compute the Galois group of this polynomial. So in application, there are abundance of application, and we are really interested in the direct Galois problem, namely given a polynomial to compute its Galois group. I like this quote of Carl Sagan that he says that there are naive question, tedious question, ill-phrased question put after inadequate self-criticism, but every question is a cry to understand the world. So, and there are no dumb questions. This is something that I really like in this quote. And in this talk, our naive question is a cry to understand the Galois theoretic world. This is the motivation for this question. And it asks a very simple question. Given a finite group G, can we find a polynomial such that this is the Galois group such that G is the Galois group of the polynomial? So it's a very naive question. It doesn't have applications, but it's something that I think most people are really want to understand because it's so basic and so natural and so simple. And this is a famous question. It's called the inverse Galois problem, and it's widely open. I think there are something like 150 years of tries to solve it, and it's still widely open. And it's a sync problem in the sense that a lot of interest in mathematics, it's simple and difficult, so it's an attractive question, and a lot of interest in mathematics is developed to attack this problem. And for example, in the studies to understand this inverse Galois problem, we develop tools that help us to understand the direct Galois problem, which is very important in applications. And it's also a step in understanding the profinite group, which is the absolute Galois group of Q. As I said, this is a very central object in number theory, maybe the most important object in number theory, at least in some point of view. And I want to understand in this talk why this problem is so difficult. Not how to solve it, because I don't know how to solve it, but I want to understand why I can't solve it and why other people cannot solve it. This is something that I want to understand. Okay? By the way, if you have any questions, don't hesitate to ask me or to stop me. Okay? So I'm going to take a probabilistic point of view of this problem that it's not important. It's not important, but it helps us to look on it in a better way. It will give us more. It's very convenient to take a probabilistic point of view, and in a probabilistic point of view, I need a random polynomial. And there are all kinds of ways to generate random polynomials. Maybe the way that we will discuss today is a more number theoretic point of view, which I call the large box model. In this case, I take a polynomial. There is a typo in the slide, I noticed. It's I equals 0 to n and not 1 to n. So there is a typo. So I take the polynomial such that the coefficients are such that the degree is fixed and the coefficients are between minus h to h. So the coefficients are in some box, and I fix the degree, the dimension of the box, and I let the size of the box grow to infinity. Okay, so this is a number theoretic point of view because it's actually counting polynomials because I choose them uniformly. Another way that we can choose that people generated random polynomials in the setting of Galois theory was more group theoretic. So maybe people here know this type of results better. So you choose some nice arithmetic group, for example, SLN Z, which is finitely generated, and then you take an element in this group in random. So for example, one way that people did it, like people like Rivin, Kowalski, Zhuv, Zavine, and Lubotsky-Rosenzweig, was to take in SLNZ is a finitely generated group. So you choose a set of generators. Maybe you put some technical condition like it's symmetric or something like that. And then you do a random walk on the Cayley graph of the group. And then after n steps, you get to some random element, and then you take the characteristic polynomial. This is another source of random polynomials. Okay? Is it clear? Okay. Another way that that is very common in probability is to take polynomials such that the coefficients are sampled in some natural way. For example, you flip a coin for each coefficient, and you choose whether it's plus or minus 1. And you let the degree go to infinity. Okay, so this is in some sense perpendicular to the previous one, because here I fix the height, I fix the size of the coefficients, but I let the degree go to infinity, so I choose more and more coefficients. And in this model, it's very difficult even to show that a random polynomial is irreducible. And there was some progress by by some people recently, but maybe I'll discuss it at the end if time permits. And another way that people are choosing random polynomial, which is in some sense perpendicular to the group theory setting, is now we choose a random matrix, but not using the group theory, but we just take a random matrix with plus minus one coefficients. And then we let the dimension go to infinity. So Eberhard just took random matrices with plus minus entries, and further Jean and Sainz Sawani, they took symmetric matrices, and they try to understand the Galois theory of the characteristic polynomial. So there are many models. I just sample some of them, and in this talk I want to focus on the first model and tell you what is known and what is not known, and what challenges do we have. Okay. So the large box model, this is the model that is the focus of this talk. So I remind you, I take the coefficient independently and uniformly from integer between minus and h, and then I want to understand what happens when h is going. Since f is random, then gf is a random subgroup of Sn, of the symmetric group. And the big question is how GF distribute as a subgroup of Sn. And a first theorem that goes back to van der Waerden, or maybe even to Hilbert, is that for most polynomial with probability going to 1, the Galois group is the full symmetric group. This is so most Galois groups are Sn in this setting. And a question that I think already van der Waerden asked is, what is the next most probable group? Is it a transitive group or is it a non-transitive group, for example? So van der Waerden conjectured that the next most probable group is Sn minus 1. So it's the group with a fixed point, which corresponds to polynomials with a root. So this was a conjecture he made in 1936. And just if you want to understand what is this probability, then the probability that the Galois group is Sn minus 1, you can show that it's the same, it's asymptotically the same as the probability that f has a rational root. And this is also the same as the probability that f is reducible. And this is some explicit constant depending on the degree times 1 over h. So it goes to 0 because of the theorem of van der Waerden, but we know in what speed it goes to 0, 1 over h. And the question of van der Waerden was, is there a group that appears with higher probability, that there are more polynomials that give you that group? And he conjectured that the answer is no. The problem is that it's, how do you check it? I mean, okay, maybe you can prove it, but how do you check it? So one way today, maybe not in 1936, is to run numerics. But the problem, let's say you take n equal 10, I don't know, your favorite number that is the number of fingers. So it's, for most people, it's 10, and you want to run numerics on that. So the problem is that there are way too many polynomials. So even numerics is very difficult to perform. And we want to understand what happens in a set that has a asymptotic probability 0. So when we run random algorithms, we almost always get Sn. So it's, even numerics is very difficult to do here. But so let's try to do numerics. And for this, it's very good if you have students, especially good students. So this is done with, the numerics is done with 2 students, Oad Avneri and Noam Pirani. And we expected for probabilities to have, so we took degree 4 because we didn't want the probabilities to go to 0 too fast. And we expect power law, so we plot both axes in logarithmic scale. So a power law, so if the probability is h to some power, we will see a straight line. And then we try to compute all kind of probability. So first, we compute the probability that the Galois group is S4. So what do we see? We took h is the size of the coefficients. So we took h bigger and bigger. So, for example, here it's h equal 10 to the fifth, which is 10,000, I think, or 100,000? 100,000 probably? It's log on the basis e. Okay, so it's e to the 5. And you see that the lower points are what is expected by the theory, which is a theorem in this case, and the upper points is what we actually get. And we see that at certain point they really look very close to each other. Okay, and then we wanted to go beyond what we know how to prove. So the second thing that we wanted is to see how what is the probability to be the dihedral group of degree 4, so of order 8. And here we also have a theorem by Cho and Dittman that gives us up to a constant that the probability goes like 1 over h squared times log h squared. So we plotted both of them, and we got up to a constant, which is multiplicative constant agreement. So again, this is a theorem, but we got an agreement quite fast. And then the next group that we wanted to check is the alternating group, A4. Here we don't know what should be the correct asymptotics. And we plot it against the square root of, square root of h to the 4. So over 1 over h squared. So we plotted this. And I don't know if you think that this is agreement or not. It depends on how far you look on it. I mean, if they are parallel, then it means that up to a multiplicative constant, they are the same. But I'm not sure that this is convincing to be parallel, but this is what we got. And the last one was V4. This is the normal subgroup of order 4 inside S4. And here again, we expect that it will be 1 over square root h less than D4. So we plot it against that, and this is what we got. And this numeric took a lot of time and a lot of effort, and when we improved the algorithm so we can go a little bit higher. And this is in degree 4. In degree 5 or 6, it becomes much more difficult to even run numerics. Let me tell you what happened since van der Waerden proved its theorem. So van der Waerden proved the theorem that the Galois group is not Sn goes to 0. And he conjecture what should be the alternate. This is the van der Waerden conjecture that I mentioned before. And then there was a series of proofs trying to bridge the gap between the van der Waerden theorem and the van der Waerden conjecture. So in 1956, Knobloch proved a power-saving bound. Namely, we want to get that the probability that the Galois group is not Sn, we want to get that it's 1 over h, so we got that it's 1 over h to some power. This was the first result. And then in 1973, the large sieve started to be developed, and Gallagher applied it to improve the bound from some power saving to power saving square root of h. So he proved the probability that the Galois group is not Sn is 1 over square root, is bounded by 1 over square root of h plus epsilon, which is some log term. And this epsilon was removed by Zavin in 2010 by the larger sieve. And in 2013, there was you see, it's roughly 40 years after Gallagher, there was the first improvement of the power saving since Gallagher. And this was done by Dittman, who used a completely different method of use all kind of fancy result on bounding on integral points on surfaces to improve the bound. Instead of h to the minus half, we want to get to h to the minus 1, right? This is the Gallagher conjecture, the van der Waerden conjecture, and he managed to improve from 0.5 to I think this is something like 0.6. How much is square 2 minus square root of 2? It's 0.6, something like this, right? I mean, square root of 2 is 1.4, so roughly, I mean. So this was a big breakthrough 40 years after Gallagher. And then something very weird happened, but I guess it's something common in mathematics, that in 1 year there were 3 big papers improving on this. And this was in 2021. So first there was a theorem, a paper by Dittman and Cho, and then by Gaffney, Lemke, Oliver, Lowry, Duda, Shaken, and Zhang, and lastly by Bhargava, which really did a tremendous improvement. So each one of these results improved on the result from 2013, but Bhargava made a huge gap. And all of these were subsequently one after the other in 2021. So instead of saying exactly what each one did, I will, because now all of them are suppressed by Bhargava, I will mention what Bhargava did. He made a big breakthrough, and he managed to go all the way to h-1. So just if you don't remember, this is the van der Waerden conjecture. The van der Waerden conjecture is that the Galois group, the probability that the Galois group is not Sn is the same as the probability that the Galois group is Sn-1, which is an explicit constant that I don't want to write, times h-1. Okay? And some people call it the van der Waerden conjecture also, but it's a slightly weaker version where you just prove that the Galois group has the same order of magnitude, that the probability that the Galois group is not Sn is O of h-1. I mean, without catching the actual constant, okay? And what Bhargava managed to prove very recently is this weak van der Waerden conjecture. More precisely, he proved 2 results that together give the weak conjecture. The first result, which is that the Galois group, the probability that the Galois group is not Sn is captured either in what we expect, the probability that the Galois group is Sn-1, or by the probability that the Galois group is An. And if you take this asymptotic, the error term is much smaller than what we want. So we showed that the second most probable group is either Sn-1 or An. And the second thing that he did, which was the really big breakthrough, was to prove that the probability that to bound the probability that the Galois group is An by O of h-1. And this was a major breakthrough, and this part, and he had to insert not only he had a lot of very strong and technical tools, he also had some very smart new ideas. So it's a combination of really ingenious argument plus a lot of proficiency in analytic number theory. So Bhargava, after essentially 100 years, proved that the probability for An is bounded by 1 over h. So if we take h, yeah. But is it really the case? So I want to understand how small is the probability that the Galois group is An. Is it what Bhargava proved? Is it close to the reality, or is it far from the reality? And I thought I will give you some conjecture. So this is a reminder of what Bhargava did. And a difficult conjecture that is going beyond a little bit beyond what Bhargava did is to prove that the Galois group, that the probability that the Galois group is An is small O of h to the -1. And this will imply the full van der Waerden conjecture. So this is very difficult because it's very difficult to go after what, I mean, the paper of Bhargava exploits this approach completely. So you need a new idea, completely new idea to get to this. A more difficult conjecture is to prove that the Galois group is actually small O of h-2. And even more difficult conjecture is to prove that the Galois group is h to the it goes, the exponent is linear in n. So here all the exponents are constant, but maybe the exponent is linear in n. And what at least I believe that the correct order of magnitude should be is that the Galois group is h to the minus n over 2 plus epsilon. And if you think about it, I mean, if h is, for example, 10, then 1 over h is 1/10, but 1 over h to the minus n over 2 is an extremely small number. So this is something that you cannot catch in a computer. I mean, it's very difficult to catch in a computer once n is difficult. So this is something that you cannot go in the street, and even if you have even if you go in China where there are 1 billion residents, you still will not be able to find the guy that has Galois group AN. It's so small. I'm not sure if it's the correct analog, but before I will explain this conjecture, let me give you naive heuristics. Why the naive heuristic is, by the way, okay. So what is the naive heuristic? We want to understand why the probability that the Galois group is AN. Now, the first assumption, which is the heuristic assumption, I don't know how to prove it, is that the probability that the Galois group will be AN is roughly the same as the probability that the discriminant of the polynomial will be a square, a non-zero square. Because I already mentioned it, that the Galois group is inside AN if and only if the discriminant is a non-zero square, and Galois groups tend to be as large as possible. So this is, I think, a reasonable heuristic assumption, although I have no clue how to prove something like this. The second thing, which is something that I even know how to prove, is that the discriminant of f is a polynomial in the coefficients of degree 2n minus 2. So when I plug in numbers, when the coefficients are of size roughly h, then the discriminant will be roughly of size h to the 2n minus 2. Now, the third heuristic assumption is the worst, because this I'm not even sure that it's correct. In fact, I know that it's incorrect. But just this is why it's naive heuristic. Naively, if we have a number of size h to the 2n minus 2, then we expect that it will be a square with probability 1 over the square root of the number, right? If we have a random number, the probability that it's a square is 1 over square root of this number. So the probability that the discriminant will be a square, we expect that it will be 1 over h to the minus n minus 1. So it says that, for example, in a box of size h, we will have roughly, out of h to the n polynomial, we will roughly have h polynomial with square discriminant. This naive heuristic is false because of the third step. The point is that the discriminant doesn't behave like a random number. It has a lot of symmetries, and this is I mean, I saw this naive heuristic in, I don't remember, in a paper or in a talk, and I did it myself also, and it seems very weird that there are so little, if I believe this heuristic, so little polynomials with Galois group AN. So together with a student and postdoc, with Ben-Porath and Vlad Matai, we looked for non-trivial symmetries, and then we got the following thing. We got that the probability that the Galois group is AN is at least h to the minus 3 over 4n. So it cannot be minus n as the naive heuristic says, and this is due to non-trivial symmetries. Let me tell you one of the symmetries. I mean, so I give you the easiest to state symmetry. So I assume that n is divisible by 4 just because it makes the symmetry slightly easier to write. And I look on polynomials that have this special form, f plus f prime equal g squared. So it's a polynomial that if I add the derivative to itself, I get a square. So what's the point? That the discriminant of f, I'm using a formula for discriminant. Discriminant is the resultant of f and f prime. And resultant is, if you think about one of the formulas for resultant as a product over the zeros of f, when I evaluate f prime at the zeros of f, then it's clear that I can replace f prime by f plus f prime. So it's the same value. And then, because of my assumption that f plus f prime is g squared, I get that it's the resultant of f g squared. And again, by taking the formula in terms of the zeros of g, each zero of g squared comes with double multiplicity, so it's the same as the resultant of fg squared. So I see that in this family, the discriminant is always a square. And how many polynomials like this I have? So the Galois group is inside AN, and I can prove that in this case, almost surely the Galois group is really AN. And how many polynomials like this I have? Okay, G I can choose freely, but I need that the size of the coefficient will be smaller than H. So if I take the size of G is of degree n over 2, and if I take the coefficient of G smaller than square root of H, then the coefficient of G squared will be roughly square root smaller than H. So I have n over 2 coefficients. I have each one of them can be a number between minus square root of H and square root of H, up to some constant that I ignore. Then I have at least H to the n over 4 such polynomial, and therefore I get H. So if I normalize, I get what I stated at the beginning. And this is very similar to something that Landsman, Lemke, Oliver, and Thorne did, but they counted number fields with with AN number fields, and they counted by discriminant. And counting by discriminant is slightly different. And you know, when you do something like this, I mean, the symmetry is so simple: f plus f prime equals g squared. So once you find such a simple symmetry, you try to look back in the literature and see who did it before, because it's impossible that, you know, all the society, all the community of Galois theory missed this symmetry. And indeed, we found very similar in this work of Landsman, Lemke, Oliver, and Thorne, this very similar symmetry. And essentially, if you go back in the literature, you can find that this symmetry appeared in a paper by some guy called Hilbert. Hilbert did it before 19,000. And even Hilbert thought about this philosophy, and Hilbert said that he saw it in a paper of Hurwitz. I didn't go back to the paper of Hurwitz, but so this symmetry was going back quite a lot. Not exactly this one, but very similar one. But still, in what we did, we put it in this scheme of probabilistic Galois theory. So it goes back to Hilbert and maybe even to Hurwitz. But still, it gave us this lower bound. And the second thing we did was to try and see, can we get better lower bound if we don't really care about the Galois group? And then we found different symmetries. I mean, we have this conjecture that most probably the Galois group is AN if given that the discriminant is a square. So we said, okay, let's focus on the right-hand term without caring about the connection. Although we don't know how to prove this conjecture, we don't even have a clue. It's a very, very interesting open problem, but very difficult. Sorry. And we showed that for the right-hand event, I mean, we find a large family of polynomials f with a square discriminant. So here we get h to the minus n over 2 minus half, which is very, very close to what at least I believe is the correct answer, but it's a naive belief that it should be h to the minus n over 2. And how did we found this? Yeah, so this is better than what I mentioned before, because here it's 3 over 4 and here it's a half. And this is a lower bound. So this is, again, it's a very simple argument. We take a polynomial which only have even, all the odd coefficients are 0. Okay, so this only works for even degree. I forgot to write it in the theorem. This is only for even degree. So I take a polynomial such that all the odd coefficients are 0. So it's a compositum with x squared. And then I will not give you the details. Then you can show that in this case, the discriminant is a square if and only if the free coefficient is a square. So I can choose all the coefficients as I like, and only the last coefficient should be a square. So the probability that the discriminant is a square is at least the probability that the free coefficient is a square. So it's h to the minus n plus 1 over 2. This is the number of coefficients. Okay? And the drawback is that in this family, the Galois group is never an. It's always a Coxeter group of type Dn over 2. I wonder, I guess that in this talk, everyone knows what it is, right? I'm trying to see. Pavel, are you nodding? Do you know what is Coxeter group of type Dn over 2?
Yes, we can assume that.
Yeah, but even I can assume it, but even if I don't assume it, it's a very simple group. It's just all the even so you take the automorphism of the graph, right? Of this graph, and you take all even elements in this. So it's a very simple group. It's a subgroup of the Richt model. I mean, not simple in the group theoretic sense, simple in the human theoretic sense. So we got a very good, in my eyes, lower bound, but none of these polynomials has Galois group AN. So this is what we know how to say. Let me talk a little bit just to let you know about what happens in other models. So let's talk about the restricted coefficient model. For example, we take I said before, take the coefficient plus minus 1, or we take the coefficient to be 0, 1. It can be with uniform, 0, 1 with probability half, or any other distribution that you want. So let's just take 0, 1 for the fun of it. So in this case, this is very recent. Under GRH in number theory, this is very known. What is GRH? It's called the generalized Riemann hypothesis. So under the generalized Riemann hypothesis, which is okay. So under the Riemann hypothesis, we know that this is just whether the polynomial is irreducible or not. We know that the polynomial is irreducible with probability 1, but we need a generalized Riemann hypothesis for this. And this is a recent result by Brouillard and Vario. Unconditional result, the best unconditional result is that the probability is, this is a number theoretical notation, the probability is bigger than a constant that doesn't go to 0. This is my result together with two co-authors, Koukoulopoulos and Kozma. So the probability doesn't go to 0. It's bigger than some number. I think probably 0.1 is okay. I mean, it's explicit number. I forgot to compute it before this talk. Okay. In these two cases, you can prove that the Galois group is AN or SN with the same probability, but in these two cases, we cannot distinguish between AN or SN. So in this setting, even under the general Riemann hypothesis, we don't know to show that AN appears with probability 0. So this is the same philosophy that if you want to understand how the Galois group distribute, so after SN, the most difficult group usually you can say something about SN, but it's very difficult to bound the probability for AN, although you know that it's small. So this is open even under GRH today. And very recently, David Hawken considered a slightly simpler case, which resembled the lower bound that I discussed before, that I did with Ben-Porath and Vlad Matai. He took reciprocal polynomials with plus minus one coefficients, and he showed that in this case, the probability to be a square is going to zero. It doesn't matter. He computed how fast, but it's important that it goes to zero. But this is for reciprocal polynomials. So as in the previous case, reciprocal polynomials never have Galois group AN. It's always an imprimitive group. Another model that I mentioned is random matrices. So if you take the matrices with 0, 1 entries, Eberhard, using the tools of Boyard-Varieux and using the tools developed for the restricted coefficient model, managed to show that under GRH, the characteristic polynomial is irreducible. And Ferber, James, Sa, and Sawani did the same for symmetric matrices, again, under GRH. And lastly, I want to say why it's so difficult. I hope that it's okay, Pavel, this picture. I thought that you will take it in a funny mood. So I want to say why it's so difficult. The inverse Galois problem, there is this joke about the guy that lost his key and he's looking under the lamp, although he didn't lose it under the lamp. So it's so difficult to the inverse Galois problem is so difficult because we only have the light on Sn, or maybe on some special families of polynomials. So we just don't know how to look on other groups. And Pavel, this picture is from the last time that you were in Tel Aviv. So, so yeah, so I think I will finish here. Thank you very much. And thank you, Pavel, for being such a great colleague all these years since I started my research. Thank you very much. And happy birthday.
Thank you, Lior, for this very nice talk and an accessible talk. Are there any questions or comments?
Well, first, I have to thank you for being my collaborator, because it was very always pleasure to work with you. But I have a very naive question. You were always talking about finite Galois groups, but can you do probabilistic methods just with infinite Galois groups? It's closer to my field.
Yes, I agree. So it depends. Sometimes you can reduce infinite groups to finite groups, like using Fratini argument or something like this. But this maybe will not be interesting because it's just reducing to finite groups. But in general, there are interesting questions about infinite groups in the setting of Galois representations, and especially arboreal representations, where you get, given a polynomial, you get an action on an infinite tree with, let's say, I mean, it's very similar to the talk we had on yesterday in the morning. So if you take, let's say, a polynomial of degree 2, you look on pre-images of pre-images of pre-images, and you get a tree of degree, I mean, the number of, how to say, of descendants is the degree of the polynomial. So you get an action on a regular tree, and the image is very interesting and has a lot of applications in dynamic and stuff. And there maybe profinite group theory can be handy, but I don't think you can really reduce it to finite groups. So you really need to use some kind of combination of group theory and arithmetic in a non-trivial way. But this is something that I'm not aware of I mean, the analog in Galois representation is the works of people like Jean-Pierre Serre and others about large images of Galois representations that use a lot profinite group theory, especially p-adic analytic groups. So maybe one can develop a theory of the relevant theory for I mean, the combination between the arithmetic and the theory of profinite groups acting on trees automorphism groups of trees to get some meaningful and important arithmetic information on compositions of polynomials. This would be, I mean, really, really amazing results, but the theory is not developed enough. This is one direction that might interest you.
Thank you.
So you should come to Tel Aviv again and we can discuss it in more detail.
Well, when I'm coming that direction, I will inform you.
Good. You're always welcome.
Okay, I see no raised hands. So please join us in thanking Lior again, please.
Thank you very much.